Okay. First, how do I say it's good morning there, right? In here we are good afternoon. So yeah, everyone. My name is Hui-Chia, and then first I wanted to sort of name our team members. We have Anna, who is a graduate student. We have Robert. He's a fixed-term assistant professor, and we have Dirk. He's also a faculty member, and then me as well. And then we are from a department called Department of Computational Math Science and Engineering. So a lot of us are doing simulations. So we are currently just right at the beginning of a software project. We call it the BESFEM, stands for Battery Electrode Simulation Toolkit using MFEM. So I want to first make it clear, like we are not developing like a mathematical solver or more like a high-level solver scheme on finite element method. In fact, we consider ourselves users. So we use the math solver to do the work we want to do. So let us begin. So I'm actually a battery scientist. So when I assume most of the audience here are not familiar with battery, right? So, but if you look at the battery, when you hear battery, typically you have this kind of three major shape, right? One is called like a coin cell, and then the other one called pouch cell. And then pouch cell is majority used in your iPhone or your computer, your laptop computer. And the other one is this called like a cylinder cells. So from the outside, they all look different, right? But when you open them, they all contain a same structure to store lithium ions. For example, in this coin cell, you have this cathode. It's a kind of like a sheet, and then you have a separator, and then you have an anode. And then what happened is actually during the charge cycling, you are moving lithium between these two sheets, right? And I like to use this one, a very simple cartoon to explain the mechanism of energy storage, right? So on the anode side, you have a graphite, and then typically lithium stays in the interlayer of graphite, right? And then lithium ion has a high chemical potential. So lithium ion want to move to the other side, which is metal oxide, and then try to insert into the metal oxide. So by moving lithium from the anode side to the cathode side, you are releasing electrical energy. And then so-called charge is you are apply or impose a voltage to lift up lithium ion's chemical potential. So lithium ion will move back from the cathode side to anode side. So that's a charge process. So this cartoon looks very simple, right? But in reality, when you open this cathode and the battery, you see this cathode sheets here, and then it's sort of comprised of many particles, and those particles are irregular shape. And then same thing in the anode side, which are graphite particles. And then this one is a typical reconstructed microstructure of cathode. You can see the particles are very irregular, and then all the empty space between particles are filled up with electrolytes. That allows lithium ion to diffuse, right? And then so first, if you want to simulate this electrochemical process, the first difficulty you want to deal is the complex geometry of the particle and tortuous channels. And then the second layer is a multi-physics issue. So if you just like look at the one side, for example, cathode side, and then you have a particle, oxide cathode particle, and then you have an electrolyte. So in the electrolyte side, you have a ion diffusion. So you have a diffusion equation for ion concentration evolution. And then you also have an potential field in the liquid phase. So you're solving this Poisson equation to get your electric field distribution. And then on the surface, you have ion going through the so-called intercalation reaction and governed by this Arrhenius type of reaction equation. And then you insert lithium into the solid particle. And then lithium will diffuse inside the particle. So you have another diffusion type of equations. And then also the solid field, you also have to solve the electro potential field. So just on one side, you probably already see 5 equations coupled together. And then you can imagine on the anode side, you have a mirror image of this. So altogether, you have 8 equations all coupled together just through the charge-discharge process. So that's the second layer of that is multi-physics. And then this equation itself, modeling is hard, but experimental side, material science community, they now has a very mature technique to reconstruct this complicated microstructure. For example, for the castle, most of them are ceramics. So they're using the technique called FIB-SEM. So they kind of cut into the sample and take SEM image. And then on the graphite anode side, it's a light element. So they use X-ray CT scan to scan through the electrode, the anode, and then you have a cross-sectional image, right? And then if you just take in all the cross-section image up in the third dimension, you are actually getting this kind of voxelated microstructure. If, for example, here, all these yellow hue are the voxels that has intensity to be 1, and then empty region is in the voxels that has intensity to be 0. So this microstructure is actually defined by a 3D array, and using very sort of widely used experimental technique, right? And then because of this technique is widely used, you can find a lot of this microstructure database. Here, I just go out to a web page. I think one is from NRail in Colorado. And then they have collected a lot of this image-based voxel data for both castle and anode. And then the other one is from, I think this one is from Switzerland. They also did a similar thing and collecting all these microstructures. And then when you go to this web page and you click to download the data, right, it's a stacked TIFF file. So you have many cross-section image, and then all of them are TIFF files, right? And then, like I said, when you, because of the directed simulation is very challenging, so most of these voxel-based microstructure data are just used to analyze the overall property of the microstructure. For example, like a porosity or the tortuosity of the channel or surface to volume ratio, this kind of microstructure property. And so if you really want to understand the electrochemical process, you will like to do simulation out of that, right? And then, like I said, because first the geometry is very complicated, so currently the model prevail in the community is called this porous electrode theory. And then the idea of that is because the microstructure is very complicated, right? So they just homogenize the entire microstructure, assuming it's a uniform media with effective material property, for example, effective conductivity of the porous media. Then in the thickness direction, you are solving a 1D problem with all homogenized effective property. And then the second dimension is there, assuming every single particle is a sphere, so that they are solving the Lysian diffusion in the radial direction. So that now you have a thickness direction of the electrode and then radial directions of the Lysian concentration. So that's also called the pseudo 2D model. And however, if you use this kind of a homogeneous model, you can get an average prediction of your battery, but you do not have any insight into the microstructure or the complex geometry. So on the other end of the spectra is you really resolve the microstructure and you solve the full-scale electrochemical simulation. But I think a lot of us know, right? If you are using traditional like finite element method, you will need to build a structure mesh to conformal with your geometry. And specifically for this kind of microstructures, it's actually very hard to build conformal mesh. And so it's a very tedious work. So what we are working on is a direct voxel-based simulation. So like I said, right, your microstructure is defined by a 3D array of voxels, and each voxel has its value. So and then we can just define the region, the pore region with voxel intensity to be 0, right? And then on the solid region, the intensity is 1. Then you have this additional parameter. You will be able to reformulate all those governing equations, now all including the voxel intensity as additional indicators. And then these are just a mathematical identity from the previous classic equation. And when you solve this one, and you pretty much will recover your solution from solving the original equation. And then the more like mathematical detail and then derivation you can find in this paper. So we are not going to go over the derivation part. So now, like I said, you have a voxel data, and then you have an intensity, and then we reformulate the governing equation, right? Then we can directly use each of the voxel as the grid point and to solve, to simulate all this electrochemical process. So here I just pick up a very simple, relative example that we did, right? And then this one is for graphite anode. And then here is a movie is showing like when lithium sort of coming in from the bottom, and then as lithium inserted into the particle, you're actually seeing the color change of graphite particle. And then, so it's original one is black, and then it starts to turn into like a very dark green, and then the burgundy color, and then very shiny gold color. So that 4 different colors are representing 4 different phases of graphite particle during the lithiation process. And then not only in the electrode dimension, you can observe these different phases. If you pick up one graphite particle and then cut through into the particle, you also see these concentric layers of different phases in each of these particles, right? And then now this one has a phase separation. So we are using this phase field model. It's called Cantor equation to simulate this phase transition process inside each of the particle. And then here, just a quick example. We try to sort of mimic a example, experimental observation of a graphite disk. And then here we have this sample, but remember this sample is defined by voxels. And then all the solving is voxel-based, direct voxel-based simulation. And then we are solving the phase transformation inside the disk. And then outside, you have an ion diffusion in the liquid, and you also solve the electron potential in the solid side and then in the liquid side. And then a quick result, you can see that within this disk, you see different layers, onion layer like phase distribution, which pretty much similar to experimental observation. So this is a sort of a demonstration of we can capture the phase transformation process. Then next one, you go to this web page and download the TIFF file. And then the TIFF file, you can pile them up. You get this 3D voxel microstructure of graphite. Then we just solve this differential equations with all this voxel intensity. And then on the left is the lithium concentration in the electrolyte. And then lithium goes in this arrow direction. And then this one is under a fast charging rate. It's in fact that we try to fully charge a graphite anode within 10 minutes. So it's a very strong rate coming in. And then on the right is the lithium concentration on the graphite particle under a fast charging rate. And lithium coming from the same direction. And then let's change to a different direction. So it's the same simulation, just rotated to a different angle. Now lithium is coming in this direction at a high rate charge. And then the simulation stop at a point that on the surface, we start to have reach a condition that the lithium metal is going to break out on the surface. So you can imagine, right, if you have a strong lithium current comes in, and if the surface gets saturated, the more you cannot insert more of lithium, and then this lithium will just precipitate outside the particle. And then if this metal keep accumulating, and eventually if it go across to the other side, and then it becomes an internal short, and then your battery will explode. So that's the point that we set up. We have to stop the charging at that moment. But if you look at this entire anode, right, you probably only use the first 1/3 of that. And then the back of the electrode, you pretty much not using it under a high charge rate. And then here is just a simulated cell voltage. And then as lithium being inserted into the graphite, your cell voltage start to decrease, until it reach negative value. And the negative value is an indication of thermodynamically plating is favored over insertion. Right, and then for this electrode, you will see you can probably only utilize 40% of the whole material, right? 60% you didn't use it. And then, so here is another design idea that is in the community, right? And then currently our battery electrode is pretty thin. And then that thickness is designed to accommodate nature diffusion within the charge time. So typically it's pretty thin, like a 50 micron or something. That's the thickness allowed regular diffusion. The idea is if you can build a very thick electrode, then you can remove a lot of this inactive material, packaging material. For example, this the plastic separator that preventing the two electrodes get contact. And then you also have a metal current collector to collect the electric current. Now, if you build a very thick electrode, you can remove a lot of those inactive material. Then you can pretty much increase your active material from 50, almost 60% to from 60% to almost 90% of your battery is built of active material. But you can imagine, right, if you have a very thick electrode, diffusion, the tortuosity channel becomes a limitation for your lithium ion diffusion. So this in engineering idea is called perfoliation. You are digging tunnels through a very through the thick electrode, so that these tunnels serve as a highway to sort of carry fast lithium transport. And then the original electrode, in the original electrode, you have this local road, right? The lithium have to travel slowly through the original region. So that's the overall idea. And then, like I said, we use this direct voxel-based simulation. So you don't need to generate a mesh. So it's very easy. You can artificially create a tunnel, right? The so-called creating tunnel, you are just setting the voxel value to be 0 within that region. So here is just an example. You are setting all the voxels within this region has a value of 0, then you're creating a tunnel. And if you do another one on this corner, this one is mimicking a hexagonal arrangement of tunnels. And like I said, right, this is all voxel-based simulation, so you can very easily to generate new microstructures. For example, here you have a no tunnel, and then you have a small tunnel, and then you increase the tunnel radius gradually over the different configurations, right? So for this very large tunnel one, you have removed almost 72% of your active material. And then it's a voxel-based simulation, so no matrix, no mesh generation. And then here is the simulation result of a no tunnel case. So when this electrode reach the plating point, you only use about 22% of your entire electrode. You have to stop the charging process. This one is another example. You have a tunnel that remove about 15.5% of your volume. And for this one, you can see lithium can reach to the back of your electrode, right? And then they have a lateral diffusion to fill up almost your entire electrode. And for this specific tunnel, you can reach to almost 60% of utilization. And here is an extreme case. You have a very wide tunnel. And yeah, you can use much more of the electrode, and you are reaching a utilization ratio to be almost 70% of your entire electrode. But you probably already noticed, right? When you have a larger tunnel, you use more of your electrode, but you are losing your materials. So if you plot the actual lithium inserted into the material versus cell voltage, so the green one has no tunnel, so it quickly dropped your cell voltage, and then more like a linearly goes to here and stop at this point when you reach plating criteria. Then you start to increase the radius of tunnel. You can see you can insert more lithium at the cutoff point. But after this point, when you enlarge your tunnel, you're actually decreasing the total lithium being inserted simply because you are losing the material, right? And then you can just plot all them together. You will see initially you can only put this amount of lithium, But by increasing the tunnel radius, you can increase the utilization, the total lesion capacity up to this point. And after it, the removing of material just decay, just reducing your achievable capacity during the process. So that here it's just a quick example about using this voxel-based simulation to find out the optimal radius of tunnels. And here just another examples. Then we just change the thickness of the electrode. And then for the first two is 55 micron and 110 micron. And for these two, digging tunnel doesn't really do any benefit, right? You just monotonically reduce your achievable capacity. That means at this thickness, the natural diffusion itself is good enough to penetrate your entire electrode. But once you go to 165 micron thickness of the graphite, then you start to see tunnel can help. And then you have an even thicker one. You can increase your optimal tunnel volume will be removing 15% of your electrode volume by this tunnel. But it actually responds differently at a different thickness. And then here is another example that we are changing the intertunnel distance, so that if you have a smaller intertunnel distance, the tunnel are getting closer to each other. And then you can also see that the optimal radius is also changing by changing the intertunnel distance. And then on this picture I show here, we actually collect the 168 set of voxel-based simulation. And then this kind of simulation is possible. It's only possible using this voxel-based simulation because we don't need to do conformal mesh building. So here, let me just summarize. So our group has been developing a lot of these voxel-based simulation toolkits. And then our in-house code, Fortune 90 or 08, using MPI. And then it's mostly finite difference based. And then here I just have a couple of selected paper that we are using the same technique to do phase separation simulation, or even with AMR. And then this one EIS is called electrochemical impedance spectroscopy simulation, or we also have a Navier-Stokes fluid mechanics simulation in this voxel-defined porous microstructure, double layer or linear elasticity or grand boundary diffusion. So the same technique can be used in many different kind of PDEs. And then our new project is we want to leverage the MFEM solver. And currently we focus on this basic electrochemical simulations, which is this BESFEM. And then we get this NSF funding to build an open source solver for these battery electrode simulations. And then when we construct this project, we sort of have two different phases, right? First phase is software development. And then the software will include in pre-processing, and then which is just importing the TIFF files, and then sort of smooth the voxel values, voxel intensity to get this psi value for our differential equations. And then once that is done, right, we have this multi-physics solver. And for example, in here, we will have to solve the lesion concentration in the cathode particle, and then in the liquid electrolyte, and then the anode particles. So these are time-dependent simulations. And then on the other hand, we will need to solve electropotential in the cathode particle and liquid electrolyte, and then the anode particle. And these are static equations. So yeah, pretty much we can just use like a conjugate gradient solver, and then also couple the two reaction rates together. So these five will be coupled together. And then after the simulation, right, we will need to do some post-processing module to visualize the data and all that. And then after the software is complete, our next phase will be the community building. So we want to let user use this software so that we will need to have a repository and build a web page and then sort of write a manual and then do some tutorial example and even host workshops. So this is the plan of our whole project. And then we are just right at the beginning. So the first stage we are doing right now is we are translating our in-house code to MFEM with compatible C++ code. So here is a flow chart of solving the coupled equation, right? These first two are the Elysian concentration in the electron and in the particle. And then this part is solving the static equation together coupled with the reaction rate. So this one is our in-house Fortran code, and then we are not going to go over with it. But we did first version is translate everything from Fortran to C++. And then we are using the MFEM as a solver to do it. So you can probably see this one, right? The P mesh and then FE space. I want to emphasize we are using it, not developing new feature of MFEM. And it's pretty neat in this directed sequential code. MFEM is doing almost the same thing as our Fortran code. So we are very happy with the first stage that we can verify the MFEM solver with our original code. And here I just show a 2D example that we just make a triangular particle image and read the pixel value and then solve this concentration in the liquid electrolyte and then the concentration in the solid particle and also electropotential in the solid particle and electropotential in the liquid phase. And then try to get familiar with this P mesh and then refine mesh and then using the hyper matrix and hypervector and then T solver and conjugate gradient solver. So everything works out and we are happy with that. But we start to notice we need to do some extra work. So we noticed that just by FEM and the difference between FEM and FDM, finite difference, we realized that FEM is much more high accuracy, but the catch is also very computational cost. So here I just give a very quick example, right? So if you want to calculate a Laplace operator in 2D, but for example, you want to calculate the Laplace at this point, you will need all 9 points, right, including the 8 surrounding neighbor points. But in the plane finite difference, you only use the direct neighbor, 4 of the direct neighbors. Then by comparison, you can see evaluating the Laplace operator, FEM is already twice as much calculation. And then if you are doing the 3D, you were using 27 points versus 7 points in finite difference. And then in the matrix, the M matrix, mass matrix, you will do the same thing. So FEM is actually high cost, but it's actually very high accuracy. So we have been doing one thing is try to use a very large mesh away from the interface between particle and electrolyte. So for example, here is we are keeping the original voxel resolution only near the interface, and away from the interface, we coarsen the matrix, the mesh to a bigger one. And then we try to weigh in the to find a balance between the computational cost and accuracy. So we have been doing on that. And then also a quick report about what we have currently. And I want to emphasize this is a work in progress now. So we built a TIFF importer, and then we also build the intensity smoother, and then we test the sequential code is totally fine. And then we are building the object-oriented version that we try to have the same format as MFEM mini apps. And then also we are working on sort of coarsen the mesh away from the interface. And then for the modeling unit, we work on building the different objects like a concentration and then electropotential and then chemical reaction terms. And pretty much this concentration evolution should have a structure very similar to example 16. And then the Laplace equation solver should be very similar to example 6. So we sort of try to build the entire code in a format very similar to MFEM example code. And while we are working on this, we sort of noticed there are a couple potential mini app we can do and then contribute to MFEM. For example, this electropotential solver itself is in fact a tortuosity calculator. So that could be the mini app. And then MFEM can also be used to do this kind of macro-homogeneous P2D model. And then we create a repository, and then we are working on that. And then, like I said, this is still pretty recent, so we don't have a very impressive result yet. And then here, I want to sort of show a fun project that the 2 undergraduate students did in the past summer. And then, like I said, this simulation result is very complicated, right? And then they work on developing the VR goggle to sort of have an examination of the simulation result. You can probably see this, the video grabbed from the VR goggle. And then that allows you to closely examine your simulation result within the complicated geometry. And we also, we will continue working on that fun part. And then I think the last slide is our developing team. And then like you will see, we only have 4 members working on this project. And then we are welcoming interesting collaborators or developer of the software, and then we want to make the software base bigger and bigger. And then, like I said, we are currently working on the basic electrochemical module, but in the community there are many interesting problems like your aging of your battery, which involves side reaction, and then during the cycling, you also have a stress buildup in your battery cells, and then you have a heat generation, and then you have a lithium metal plating on the electrode, etc. So these are a lot of add-ons that we can sort of expand the MFEM software to become a very widely used community code. And then, so we want to recruit users and developers in this project, and then we put the email here and contact information. So if you are interested in to get into be part of this electrochemical simulation part, and you are welcome, and then please let us know. So with that, I will stop my presentation here.